Let us look at proposition number 25, 26 of works of Archimedes, specifically from on conoids and spheroids. The proposition says in any hyperboloid of revolution, if A be the vertex and AD the axis of any segment cut off by a plane, and if CA be the semi-diameter of the hyperboloid through A, CA being of course in the same straight line with AD, then the ratio of segment of the hyperboloid to the cone with the same base and axis is the same as the ratio AD plus 3 times CA and AD plus 2 times CA. So let's see how we can understand this. So let's cut off a segment of the hyperboloid of revolution. Let's draw a plane through the axis perpendicular to this. So we have this. Now you will notice that this plane cuts the hyperboloid in a hyperbola, and this plane intersects this plane here. Let's call this B and this as B prime. Now here B prime are the points of intersection between the hyperbola and this line of intersection. The axis and this intersection B prime intersect each other at D. A is the vertex. AC is the semi-diameter. What we are going to do is AC, we will take this length and cut off a segment here at A prime. Again, we will do the same thing at H. So these three segments are equal to each other. That is, AC is equal to A prime C is equal to A prime H. Let's draw a tangent parallel to BB prime through A. Let's call this as EF. And let's join BE and B prime F. Around this, we can draw a cylinder and we can draw a cone. So to keep the diagram a bit more, easy to read, I'll remove this cone. So here, what the proposition is saying is segment of the hyperboloid is to cone with the same base and axis, that is this cone, is equal to AD plus 3 times CA, which is nothing but AH, is to AD plus 2 times CA, that is nothing but AA prime. Okay, so which means instead of this ratio, we can take the direct AD plus 3CA gives us HD. So we can say HD is to A prime D. Okay, anyhow. Now we cut off equal lengths in AD. So basically we are going to slice the cylinder. So first we will mark these equidistant points and then we will draw lines through these points parallel to BB prime. Now we are circumscribing and inscribing figures, and we have this rectangle which represents the inscribed figure and this rectangle which shows the circumscribed figure around this hyperbola. As I mentioned, this can be written as HD is to A prime D. Let V be a cone with the same base such that V, volume of V is to cone ABB prime is equal to HD is to A prime D. If we take a cone like that, then volume of V is equal to volume of the hyperboloid segment. Okay, let's continue the construction. Now we will extrapolate this volumes into areas of rectangles. So let's take A equal to AA prime, AA prime. Let's take B is equal to AD, AD. So that means these two together will form what? A prime D. Now on B, we draw a square and we complete the rectangle. So this is B because it is a square, and this is A. So this area would be A times B. Similarly, we take P, or we draw P square on this along B square, where P is equal to AN. Again, we complete the rectangle. So here the rectangle would be A times P. Next, we take Q square, where Q is equal to AM, and we complete the rectangle AQ. Similarly, next slice, R square, and we complete the rectangle AR. And finally, L square, where L is equal to this A capital L, and we complete the rectangle. So now what happens is, if we look at these two figures, we get A times B plus B square, A times P plus P square, A times Q plus Q square, A times R plus R square, and finally A times L plus L square. Now we create a separate rectangle whose area is equal to AB plus B square, or we can say AD times A prime B. Okay, now let's look at the proof part. Let V be a cone with the same base as cone ABB prime, such that V is to cone ABB prime is equal to HD is to A prime D. This we have seen in the previous slide. Then V is equal to segment of hyperbola. Now we know cylinder is to a cone with the same base and height has a ratio 3:1. So that means cylinder is to EB prime is to V is equal to A prime D is to HD by 3. So now let's assume that V is not equal to segment of hyperboloid. That means it has to be either less or greater. So case 1 will be, if possible, let segment of hyperboloid be less than V. Now what we'll do is we will circumscribe and inscribe figures around the hyperbola such that circumscribed figure minus the inscribed figure is less than segment of the hyperboloid minus V. Now, which would mean inscribed figure is greater than V, since circumscribed figure is greater than segment of hyperboloid. Now, let's extrapolate the volumes of these slices to these rectangles. So here A is equal to A prime, B is equal to AD, P is equal to AN, Q is equal to AM, and finally L is equal to AL. The rectangles formed are AB plus B square, AP plus P square, AQ plus Q square, and so on till AL plus L square. Now AB plus B square is equal to AD times A prime D. AP plus P square is equal to AN times A prime N. AQ plus Q square is equal to AM times A prime N. So that finally we have AL plus L square is equal to AL times A prime L. Let S be the rectangle AD times A prime D. So now let's do the comparisons. First frusta in EB prime, that is first frusta means this, is to the first in inscribed figure is equal to BD square is to PN square. This is one of our previous propositions. We have already shown this. First frusta in EB prime is to first in inscribed figure is equal to AD times A prime D is to AN times A prime N. Again, in a previous proposition, we have shown that BD square is to PN square is equal to AD times A prime D is to AN times A prime N. But AD times A prime D is S, and AN times A prime N is equal to AP plus P square. So we can say first frusta in EB prime is to first in inscribed figure equal to S is to AP plus P square. Similarly, we can show for with respect to the rest. So S is to AQ plus Q square. S is to AL plus L square. The last frusta in EB prime, this is the last frusta, has no corresponding inscribed figure. Here there is no inscribed figure. So cylinder EB prime is to inscribed figure is equal to S is to AP plus P square plus AQ plus Q square and so on. From proposition 2 of on conoids and spheroids, cylinder EB prime is to inscribed figure is greater than A plus B is to A by 2 plus B by 3 based on this construction. So cylinder EB prime is to inscribed figure is greater than A prime D is to HD by 3. A plus B is A prime D and A by 2 plus B by 3 is equal to HD by 3 again from proposition 2. A prime D is to HD by 3 is equal to EB prime is to V. So cylinder EB prime is to inscribed figure is greater than cylinder EB prime is to V. Here cylinder EB prime is there on both the sides of the inequality. And there it is the numerator in both sides. So that means if this inequality that is greater than has to survive, then inscribed figure has to be less than V. We started off by saying inscribed figure is greater than V. So which means there is a contradiction. So we can say segment of hyperboloid is not less than V. So one case we have shown that it is not true. Now let's look at the second case. If possible, let segment of hyperboloid be greater than V. So now we circumscribe and inscribe figures such that the circumscribed figure minus the inscribed figure is less than V minus segment of hyperboloid. What this means is, here inscribed figure is less than segment of hyperboloid. That means to maintain the inequality, V has to be greater than circumscribed figure. Okay. So now first frusta of cylinder EB prime is to first in circumscribed figure. If you notice, the circumscribed figure and the first frusta are the same. So we have the ratio S is to S, which can be written as S is to AB plus B square. Second frusta of cylinder EB prime is to second in circumscribed figure is equal to S is to AP plus P square. And so on for the other frustas. So cylinder EB prime is to circumscribed figure is equal to S is to AB plus B square plus AP plus P square and so on. So cylinder EB prime is to circumscribed figure is less than A plus B is to A by 2 plus B by 3. This is from proposition 2 of on conoids and spheroids. Again, here A plus B is A prime D and A by 2 plus B by 3 is equal to HD by 3 from the based on the proposition 2. But A prime D is to HD by 3 is equal to cylinder EB prime is to V. So cylinder EB prime is to circumscribed figure is less than cylinder EB prime is to V. So here again you notice cylinder EB prime is there on both sides. It is the numerator on both sides. So to maintain the inequality, what should happen? Circumscribed figure has to be greater than V. We started off by saying what? V is greater than circumscribed figure. But here we are saying circumscribed figure is greater than V. So which means there is a contradiction. That means segment of hyperboloid is not greater than V. So it is neither less than V nor greater than V. That means it has to be equal to V. So if it is equal to V, that means this statement holds. The volume of V is to the volume of cone ABB prime is equal to HD is to A prime B. But what are HD and A prime B? HD is AD plus 3AC and A prime D is AD plus 2AC. So and V is equal to segment of the hyperboloid of revolution ABB prime. So we have finally shown that segment of the hyperboloid ABB prime is to cone ABB prime is equal to the ratio AD plus 3AC is to AD plus 2AC. So that was proposition number 25 and 26 of works of Archimedes, specifically from on conoids and spheroids. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.